Welcome back. Uh, Sorry for rushing through the break, but we are severely behind schedule, so that's why we need to get started again. So next session will be on fine-tuning algorithms and approaches, and that will be covered by Mehan Kamakoti and Padmanabha. So Mehant is a research software engineer at IBM Research. He's currently part of the hybrid cloud platform team, where he's working on conveyor move to cube, AI for code, and systems for AI. He is interned at CERN, IBM Research Lab, and Core Lab in Sri Lanka. He has graduated from NIT Andhra Pradesh, and he has worked on video anomaly detection, computer vision, machine learning, and databases. So over to you. And Padmanabha is a research scientist at IBM Research, and he works on GenAI platform fine-tuning and platforms, and he holds several patents and publications in app modernization, hybrid cloud, and AI domains. So, yeah, all yours.
Thank you. So previously, we have seen a talk on data preparation. So it's a very big task. So afterwards, subsequently, what we do is basically train our model on that particular data. So we'll be covering that in the slides. Okay, so here's a very high level view of stages that are involved in training a language model or a generative AI model. So essentially, if you look at here, there is some reason and intuition behind dividing each phase into a couple of steps like this. And we'll go through that in the, the upcoming slides. So one thing to notice here is as you move from left to right, as you progress, the infrastructure budget could decrease, the cost would fall, and also the data becomes more specialized, as in you move from pre-training to fine-tuning. So let's understand the intuition behind pre-training. So let's say that you have a language model with random weights and you give it some text. So you would often see it give out some garbage random set of characters. So essentially there you would like to actually make the language model learn a couple of things, the vocabulary and also the language constructs, right? So like grammar, in English you have idioms, etc., stuff. So you want the model to learn that. So that's where you would do a pre-training where you take a large corpus of data and you do unsupervised learning over that large corpus of data. So why do you do that? I've covered it. And how do you do that? It's pretty much like a simple training loop, forward pass, and then you get the outputs, you do loss calculation, and then optimize the step and backward pass. So it's pretty much the same traditional old training loop, but there are a couple of things different here. So first thing is the objective, what we're trying to do here, right? So we essentially do, in most cases, we do a next token prediction. There are other objectives like mass language modeling, etc. But this is pretty much widely used modeling based technique. So what we are doing in next token prediction is essentially given, let's say, tokens T1 to Tn minus 1, you are asking the model to predict the token Tn, and then you know what the token Tn is, and then you calculate the loss. So each token prediction from the language model is more like a classification task. So you have a vocabulary, and the model has to generate probabilities for each of the token within the vocabulary. And then you basically, it's more like a classification task there. And then you know which token you want to prioritize there, which class you want to prioritize. The class here is the token. And you do any classification loss like cross entropy loss or log loss, etc. Cross entropy loss is widely used. Fine tuning is also pretty much similar to pre-training here. The only difference is that in the data, basically, it will be in less amount of, in terms of the number of samples, it will be less. And secondly, you do a supervised learning here. Basically, the data will have question and answer pairs, etc. And why do you do that? You want to actually align your model to your downstream tasks. So when you do a pre-training, in the pre-training phase, your model learns the vocabulary, constructs, etc. But it may not learn the downstream tasks that you're really trying to do. So we'll cover some use cases in the upcoming slides to differentiate between in this particular angle. Um, how do you do fine tuning? It's pretty much same as the pre-training, but there's a couple of differences here. The first one is you calculate loss only on the output tokens and not on the input tokens. So what do I mean by that is you really don't want the model to learn the question, rather you only want to make the model learn on the output or the answer to your question. So that's the difference. Again, you can do causal language modeling here, mass language modeling, but yeah, causal language modeling or the next token prediction is widely adopted. So first use case scenario, let's say you have a Kannada text here, which actually means how are you and I, and you pass it to language model and you expect it to generate a fluent subsequent set of characters which can fit properly to the previous text. So if that was your task, then the model has to actually understand the language constructs and also the vocabulary of Kannada really well. So that's where your pre-training comes into play. So you can simply pre-train your model on a very large corpus of Kannada text. Of course, going through all the data processing steps that we discussed in the previous presentation, and then you pre-train the model on that in an unsupervised manner. So the in many cases, language model of a decent size would actually generate this fluent text after pre-training on a good amount of size. So let's say in the previous step, you have a language model that you have checkpointed, and now you really are interested in English as well. And you ask the same question, how are you, I? And you wanted the model to complete it saying, I'm fine. So in that case, of course, the data that we used previously was all Kannada. So of course, we don't really expect the model to generate any English text there. So there you really want the model to also learn the vocabulary of English and also the language constructs of English. And another important thing is the language constructs of English differ from the language constructs of Kannada. So you need to do an extended pre-training here, where you essentially continue the pre-training phase of the language model on a freshly available English text. So this can deteriorate performance on the previously seen Kannada data as well. So there can be many techniques that can be employed, like kind of ensembling data, etc. But we can discuss it. We're not covering that in this particular slides. So this covers how extended pre-training would look like. So let's say you want the model to do some task for you. So you want to do a translation task from English to Kannada, and wherein the English text that you give is how are you, and Kannada, it has to generate some Kannada text, which is merely the translation of how are you. So like you've seen before in the past, in the previous two use cases, you want the model to have understanding of Kannada and English. And now you also want the model to understand the task that is basically conversion of English to Kannada. So in many cases, the model might fail. In many cases, the model might fail to actually generate a right translation for the English text that you are intended to have. So in that case, you would like to actually fine tune it downstream. Okay, so that's where the fine tuning phase comes in, where you want to actually align your model to a specific downstream task. I'll hand it to Naba to cover the rest of the slides. Am I audible? So thank you, Mehan, for. So now, so far we have seen what pre-training is, what fine-tuning is at a high level, and how they are related and why they are supposed to be done. Now we will look at the tuning in more detail, the tuning landscape. So the first approach that we will look at is full fine-tuning. So full fine-tuning is a step which is, as Mehant mentioned, is very similar to pre-training. The idea is that you have to update the entire set of weights that are there in the model.
So basically, this is a neural network model, right? It is an advanced version of neural network model. So the weights have to be, or the entire set of parameters space or the weight space has to be updated, which will be heavy, quite heavy in terms of resources. So, but what we will be doing is when we are doing fine tuning, we will be doing it on a specialized domain or data related to a specific domain or a particular set of tasks or a specific set of curriculum. So because of that, the resources might be less because the data might be specialized and less, but compared to the pre-training, but still it is significant. So um, in order to alleviate this problem, there are a series of techniques that are there, which operate at various levels, which can help achieve the same task of specialization with minimal reduced resource footprint. First thing is in context learning, where you actually don't really train the model per se in terms of modifying the weights, but rather what we do is when we are prompting the model, when we are asking questions, we provide examples and context to the question so that the model can learn from that prompt itself what the answer should be. So this is in context learning. So here the training itself is not there. It's more towards the generation stage. Then there is I'll cover prompt tuning and I'll go back. So in the prompt tuning phase, it's similar to in context learning, but here if you notice um, this part, the tunable soft prompt part. Here, what happens is there's a set of text called soft prompts, which are attached to the input text and passed to the model, so that it generates some answer. And based on that, the response of the model, the feedback is used to tune this soft prompt, so that the next text that is brought in can be get a better context, so that the model can learn from the context and the prompt and then get better and better. So here the weights are not changed, but the prompts are changed here. And a part of the prompts are reserved for tuning. So this is called prompt tuning. Then there are two other techniques which also help in reduced footprint. Here, in the previous two cases, we are not actually changing the model weights. But in this case, also we will not be changing too much of the model weights. But what we are doing is there is something called low rank adaptation. So the weights, when they are updated, there is a delta, that is a delta of the weights that need to be added, so that the changes to the weights are then reflected and used for generation. So the delta is what is being trained here, and it is the delta weights, the delta W is decomposed into two smaller low rank matrices, and then those are updated, so that the update phase will take less resources, and you need less GPUs for making this happen. The QLoRa is similar to LoRa, except that the quantization is applied, so that you will have a much lesser footprint than the actually full precision approach. So these are the LoRa and QLoRa techniques. And they all fall under the parameter efficient scheme of techniques. So when to use what? So we start with in context learning, and if it satisfies our requirement, we can arrive at that based on the evaluation bench. So we can have an evaluation data set, define our metrics, and perform in context learning using prompts. And if that satisfies our requirement, the evaluation will give a good result. Then our model is ready. Maybe if that doesn't help, then we have approaches for parameter efficient tuning, where under low resource footprints, we can use techniques like LoRa, QLoRa, or prompt tuning. If that also doesn't work, then we go on to fine tuning. Now, when we are obliged to use multiple GPUs in the case of full fine tuning, for instance, then we will have to use multiple GPUs, maybe even multiple nodes. Then what should we do? Then we have to go to distributed training, because in order to leverage the utilization of the GPU, you have to train using multiple GPUs, right? And you have to manage your training process across these GPUs. So that's where distributed training comes into play. And if you look at this graph, as the model size has increased significantly, the gap between the GPU memory and the requirement of the model is increasing. So that means that distributed training is inevitable in most cases. So there are different techniques of distributed training. So the first of those is data parallelism. So in this particular case, the data that is there, that is split apart, but the model is kept as same. And every GPU will have a copy of the model while the data is split and sharded and passed in pieces to each of the GPUs. So each GPU will actually learn on a different set of data, but the same model. Now, once they get the weights, they will synchronize with each other to share the weights and then update each other. So, but there is a limitation here because the entire model is stored in every GPU, which might not even be possible many times. So that's where techniques like fully sharded data parallelism come in, FSDP. in this particular protocol, the distributed data parallelism is used, but the distributed data parallelism is used. But here, the sharding techniques are extended to the model layers and the weights. So if you notice here, given a set of layers, the layers are sharded, and these shards are stored in different GPUs. So that means each GPU will not keep the entire model, but it will keep shards of the model. And when I say shards of the model, it could involve things like the optimizer state, the weights, and the gradients and such, right? So each GPU will have a piece of that. And when the training is in progress, these pieces are either collated together, and then that particular layer is used to is materialized, and then it is applied on the set of weights to perform the computation. So this is a FSDP protocol which does something like that. So in this case, it's not every GPU is not holding the entire model, but shards of the model. That's the key point here. Then there is tensor parallelism, where going down to the level gradients of the degree of the layers, sublayer granularity, where each layer is broken into even smaller pieces, where the small submatrices that constitute the layers, that they are distributed across the GPUs, and they assimilate. I'm sorry, the computation is applied on them, and then the data is the resultant of the computation is then synchronized between the GPUs, and then the entire thing progresses across layers. So in this case, the key point here is that every GPU is not holding not even a layer, but only parts of the layer, the submatrices. And then when the computation happens, the communication between the GPUs has increased here. But the memory required per GPU is less, much lesser than the previous case. So this is an example of tensor parallelism. You can see here that the original matrix A, which was supposed to be multiplied with X, is broken into two parts, and then multiplied separately, then broadcasted, and then the results are then again combined with the second matrix B, and so on, and then all reduce operation combines them. So this all reduce broadcasting, these are all the communication overhead that this will entail. So now we have looked at some of the parallelism approaches. Let's look at the tools that are there in open source, and maybe in, as platforms, software platforms that can help us fine tune using these distributed training mechanisms under the hood. So without the user actually knowing what is happening, we can conduct a training, because these are all very complicated protocols. So to know them is itself a large learning curve. So can we do it better by using tools which are off the shelf, and then just get it done by running a single command or maybe a graphical user interface. So there are tools for that. So the first tool is the open source IBM tuning stack, which is actually open source. You can contribute to this. And this supports all the techniques that we just discussed: full fine tuning, parameter efficient fine tuning, LoRa, QLoRa, prompt tuning, and so on. And it supports multi-node, multi-GPU training. So it also has mechanisms to control the training using the trainer controller framework. There is monitoring capability to monitor the loss of the progression of the training loss, evaluation loss to the AIM dashboard. So these are the various capabilities that this particular tool provides, and it's open source. You can try it out. If you have the infrastructure, you can try this out and then play with it. Then there is the IBM Watson X tuning platform. So this also is a product from IBM, right? And this can help the user spawn tuning jobs and then get the result, get the models, then maybe compare models, and all those things can be done here. Simplifies the task for the user. Then there is the Instruct Lab framework. So this is also open source. Now here, the nice thing about Instruct Lab is that it allows for synthetic data generation based on the, so users can contribute the skills that a model has to learn, and based on that, it's reviewed and added to the Instruct Lab backend, and the backend will use this repository of skill requirements to generate synthetic data, which can be then used to train a model to learn those skills. So this huge flywheel of development can help in training models for community shared skills, so that the model becomes more democratic.
Custom models, this is a way to go. So I would encourage you to look at offerings, this open source stack from IBM, and try to play around with it and see what new skills you can bring or build on top of the GenAI models. Yeah, thank you.
To add to what she said, the nice thing is the data is generated by the this framework, so you can worry less about the data because it's getting generated here synthetically, and you can use it to train models, right? So that's the other advantage that this framework has. So some research directions that we think might be interesting in this space is planning and intervention, experiment planning and intervention. The idea is that when you are conducting as a user, if you are conducting experiments to train models and so on, you would want to think of what sort of I think one of the previous speakers mentioned, I think Shailaja mentioned about you training the model until you get a better accuracy, right? So you would that means the model goes into several phases of training. So it could be pre-training, extended pre-training, then further fine-tuning, maybe many layers of fine-tuning and so on. So when there is a journey involved, you would want to plan the journey ahead of time in terms of resources and infrastructure, right? So how do you plan it? So that's experiment planning. So planning would involve planning for the multiple stages, what stages should be there and how they should be configured in terms of mix of data that needs to be used, parameters, hyperparameters that need to be used for each stage, managing the context of the data that is being passed to the model for training and so on. So and then there is also the intervention. So when you are doing the training, you would also want to know how is the training going on well? Are there bugs in the training? Is the training introducing anomalies into the model, model's capability? All these things need to be analyzed and automated as much as possible. So this is a space that we are looking into in this particular domain. So if anybody is interested in collaborating and so on, we can consider speaking about it. So that's about yes, and there are a few demos that my colleague will show.
Not doing any live demos today, but I'll be going through a recording here and kind of explain what's happening here. So two things I want to show is I'll quickly show the resource consumption between among different techniques that Nabha has explained before, and then I'll explain what arguments are going into this particular tool. So the tool that we are showing here is the FMS HF tuning, which Nabha has actually spoken about, and is also open source. So okay, so if you see here, right, I'll just use this as a snapshot. So if you look at here, so if you look at here, this is a distributed training which uses FSDP that Naba has spoken about, which essentially leverages two GPUs. And we see a memory breakdown between the two GPUs here, which is almost equal, around 47, 46 gigs of memory usage. And you see a speed of train samples per second around 13.6 samples overall. Okay, so kind of clear difference I want to show among different techniques that are involved. So this is something we have for FSD. So let me show for the other technique. Okay, so the same setup, just that we are removing FSDP out of the picture and doing a single GPU training run. And I'll show you the memory and basically the memory and time estimate. Okay, so if you see here, the memory, the forget about this. This is a kind of a buffer which has been there in the previous process. But if you look at here, it just uses one GPU, and the memory it has been using is around 80 gigs. It's almost like double that you have seen before. And this is a single GPU run and exact same setup, same model and same data parameters as well. And I'll show you the train as well, the TPS as well. Okay. So if you look at here, the train samples per second is around 7.42, which is like half of what you've seen before with FSDP. So since you're doing a data parallel among between two GPUs, you're essentially getting a 2x speed up with FSDP as compared to you're doing in a single GPU setup. And also on the memory side, you see the memory is divided into half when you're using FSDP two GPU setup as compared to single GPU. So this kind of a benefit that you get, let's say you might also get into OMs when you not able to fit your training experiment setup on a single GPU. So that's where the distributed training schemes come into play. So let me show you one more technique. So this is essentially the LoRa, low rank adaptation technique that Naba has explained. So here we essentially kind of train only some subset of layers. Basically the delta, we store it within the, which we call it as adapters to small matrices. And we try with the same setup, the same model, and also the same set of data. You see the difference, clear difference in memory and also the throughput. Okay, so here I'm trying to add adapters to all the linear layers in the large language, the language model that we've been using here. So because of that, most of the layers are linear in the language model. So we don't see much of the memory gains here, but you see significant as compared to single GPU, right? So single GPU you've seen around 80 gigs, and here you see around 50 gigs of memory that has been utilized. And if you look at the train samples per second, it again stays at similar to how much that you have seen for a single GPU training. So you don't lose out much there. It also makes life simple with less amount of memory usage. So these are three techniques I just wanted to show in terms of how it differs from memory and throughput. If we have more time. Okay, so I'll quickly go through the training arguments. Just give me a second. So let's go through the training arguments here quickly. So yeah, so you see here we have been using Torchron here. It's a distributed process launcher. Usually, whenever you want to launch any distributed training, you can use Torchon from PyTorch. So it kind of exposes certain API functions here. For instance, you can do multi-node training, multi-GPU training, etc. So it's more like a single instruction multi-data setup. So it follows that particular paradigm. So you essentially provide the number of nodes there in the particular process group, and also the node rank where that particular subgroup is running, and also the number of processes per node. So these are pretty trivial set of kind of easy set of arguments that you need to pass in order to run any distributed training. So here comes the FMS HF tuning training script, which is essentially the tuning script that you see here. SFT trainer.py. There's a lot of documentation on how to use it, so you can use it, and also there's a lot of documentation on different arguments that it supports. But few things I want to bring it to your notice is the couple of them. Like for instance, you can pass in the model name or path directly from the Hugging Face model ID. So we've been using here Granite 8B code model. And also you can pass in all the typical training arguments like learning rate, number of training epochs that you have, the data path, the torch D type, the data type of the model that you want to load in, and also the training logging steps, logging strategy, flash attention, you want to use flash attention or not, etc. So you can pass in all these arguments. There are a huge number of arguments and features. You can see it in the documentation as well. So as opposed to the previous one, which is multi-GPU training, here you see a similar set of arguments, but a couple of them would change. So right here, okay, just didn't show up yet. Okay, I'll cover the LoRa first. Come back here. Okay. Yeah. Okay, so LoRa, you see there's certain set of flags that you additionally add in order to turn on LoRa here. So you PEF method, we support prompt tuning, LoRa adaptation, etc. So you provide what method you want to use, and also subsequent LoRa flags here, which target modules you want to add adapted to. Basically, those are the modules contribute in the gradient calculation, and also the rank, the matrix rank that you want to use in the decomposition. So when you do a low rank decomposition, what should be the dimension, one of the dimension of the matrix? You can also provide that, and there are other LoRa arguments that you can use. So it's pretty easy to use. You just pass in the flags and then you run it and things should work. Yeah, I think that should be good. Thanks.
Thanks, Mahant and Naba. Any questions?
Just a query. In terms of figuring out what is the best number of GPUs to be used to be tested against such a scenario, is there a formula for that, or we keep looking it up?
So, well-known decoder architectures, in fact, encoder decoder architectures, there are papers from NVIDIA, etc. They also have, they essentially have derived some formulations, theoretical formulations that you can use in order to kind of estimate how much memory your model might need. But from my experience, we see that the theoretical formulations actually differ a bit from the actual memory consumptions that they take. So yeah, they're a good starting point, I would say. I mean, there are formulations. Yes. Was that the question? Or?
That is, just to extend it slightly with Granite series, we have quite a few different variants of the Granite models that are available. And when those are to be compared across, what are the standard number of GPUs that we want to really test it out on?
Okay, so Granite code models, so we have an interesting session right after. So you will have all the information on Granite in the next session. But if you boil down, right, Granite is a decoder architecture, and it boils down to the number of parameters that each of the model has. We have a wide range of offerings from 1 GB to 2 GB to 2 billion parameters, 1 billion parameters to 8 billion parameters, and going forward as well. So it depends on the size of the model that size of the Granite model that you use, and based on that, you would need to choose the memory requirements that you might need. And also, of course, on your training setup, right? If you have a larger batch size, you would essentially need more memory, larger sequence length, more memory. So depends on that as well. Was that the question? Anything did I miss?
And one last question.
Yeah.
Sorry. So There is system prompt also that we can actually set
Yes.
out. Is there some things that this kind of a test stack tuning could actually help us figure out? What are the best system tunings that are already available for such kind of parameter models altogether?
Yes. So Granite has a system prompt. I hope it gets covered in the next slide. But we have a paper, Granite paper. There uh, we have actually mentioned the system prompt, which works well. Um, uh, but choosing the right system prompt through tuning, I don't really understand how that works. But mostly the way system prompt works is there are two ways. One is basically the thing that you use while pre-training, and second is by trial and error. So whichever works, right? So most cases, the paper actually gives you the system prompt to use. It's on archive.
Llama series, they also have a very good paper, which actually speaks end to end about every aspect of training, fine tuning, instruction tuning, and all those things. So that's one good paper. And Granite 3, they also have a paper that is published, and they also speak about every aspect of the Granite training. What the data that was used, how the instruction tuning happened, how was the data mix determined, what sort of batch scheduling algorithm was used, and so on. So it's quite informative. That also you can, yeah, I can share the link. Once again, thanks.
So the last session before the lunch break, I hope you have enough energy to hold on, is by Felix George, and he's going to talk about inference serving and optimizing inference serving. Felix is a research engineer, software engineer at IBM Research, and he works on sustainable computing, observability, SRE bench design, and development. He is a graduate from NIT Calicut. Over to you, Felix.
Am I audible? Hi, everyone. So you learn how to, prepare the data from Shailaja, and you learned how to train the model from Mahend and Nabha, right? So now what to do with the model, right? Like you want the public to use it, or you want yourself to, others to use it, use your trained model. And now how do we do that? Like we are going to learn about the inferencing part, where you host your model in some cloud, or you have your own infrastructure for hosting it. How do you optimally use the infrastructure to inference your model? Or how do you enable the public to use your model? So LLM inferencing, it's an autoregressive transformer model where you are sending it a request. You tokenize the CPU will be tokenizing the request, and you generate token by token. Like your input, whatever the output you generated, you feed it to the model again, and till the end of sequence is reached, it will generate the tokens for you. So this is a simple thing. And now in the inferencing, the challenge becomes when there are multiple people are there and there are multiple users. Okay, so as you all know, GPUs are really expensive, and how do you batch the multiple requests from several users together to serve optimally? Also, you have to look into user considerations, like they want the tokens to be coming fast. Like if you are using ChatGPT, you don't have to wait, right? The generated tokens keep on coming. So those are the challenges when you have just one user and you have multiple users. You have to do the appropriate batching.
So the request gets, processed in GPU simultaneously for all those requests. So these are some, inference engine available in the market. So the really popular one now is the VLLM, and this is the performance comparison. So now you have several engines available in the market, and so you have to make most out of them, right? Like, so we do compare, measure the performance of them, and usually we use the token throughput, like how much tokens it can generate in a unit time. So as you can see here, there are in the x-axis is multiple models, and y-axis is the token throughput of different inferencing engines. So as the model size increases, the inference time to decode, time to generate tokens also increases. So here it shows that VLLM outperforms most of the, all other inference engine most of the time. So we are using GPUs. GPUs are really expensive, and what GPUs are really good at are parallelizing some tasks. Okay, so now you have multiple requests, and you have to generate tokens for them. So some of these were covered in the earlier session, like data parallel. So here I'm just saying how it is used in inferencing part. Okay. In earlier session we learned in how they are used in the training. So data parallel is when the model is, you keep the same copy of the model in multiple GPUs. So consider it like horizontal auto scaling. If you have enough GPUs, the request can go to either of the GPUs because the model is in all the GPUs. Okay, and basically you can increase the number of users by doing so, but this is not very efficient because you have to keep the model in a replica of the model in all the GPUs. Okay. The next one is tensor parallelism. This take advantage of the matrix multiplication algorithm, like have to multiply the row with the column. So and you can sum it up later also. So this is where the parallelism of the GPUs can be efficiently used. So you take one layer of the model, you split it into n slices, where n is the number of shards or the number of GPUs. Okay, each participating GPU will contain a shard, and shards are separately processed. And after end of the multiplication, you have to combine the data, have to sum it up everything. That is so this is the equivalence diagram. Like you have to multiply these two matrices, and it is equal to multiplying individually and then summing it up. Okay. So this tensor. So here there is a communication overhead between the participating GPUs. So this overhead will be minimum when all the GPUs are belonging to the same node. The next technique is pipeline parallelism. So here the model, you can split the model vertically, like suppose the first 3 layers belong to the one GPU, and the next layers belong to another GPU, like you are splitting it vertically. So here the problem with the pipeline parallelism is like only one layer will be active at a time. So there will be GPU idle times. So here also there will be communication involved between the GPUs for syncing up. Pipeline parallelism is mostly used in the training, and inferencing you hardly see it. Okay. Now there are some inference specific optimizations that we use in the GPU. Okay, so first one is continuous batching. Here what we try to do is, suppose these are the GPU states, okay, at different time instances. Now you have you can fit 4 requests in the GPU memory, which is the DRAM, GPU DRAM, and here you want to so earlier what the system used to do was, you have an inference engine, you take some request. Okay, suppose there are 4 users, you take the 4 requests from the users, and you give to the GPU for decoding, right? Iteratively it will be generating each token. So the yellow tokens are the input request from the user, and the blue one is whatever is generated. So after first decode, for all the requests, 1 token is generated. Okay, and you are not adding any request in the vacant space. Like you are just reserving it for the future generated token. Here as you can see, after at the T6, the first request is generation was completed. Okay, now you because of the early system used to wait till all the request generation was completed. Here till T8, these requests had to wait whatever completed earlier. For example, T5 S3 was completed, and T6 S1 was completed. Also, these requests had to wait till all the other sequence in the batch to reach end of sequence token. Then only the request was taken out of the GPU. In the continuous batching technique, as soon as it's a token to token decode, where as soon as a request reaches end of sequence, you take it out of, and if you can fit another request, you do that. So that is what is happening here. As soon as at T5, when S3 was completed, you inserted S5 here for a new decode. Okay. So here the wait time of the request decreases, and it gives you better throughput, lower latency, all the interesting things you want. And the second one is the quantization. Here, okay, so you are trying to load the model, right? So the model will take a chunk of memory of the GPU. So for example, a Llama 8 billion model will take around 15 GB of the GPU memory. So whatever rest or whatever memory is available after the model is loaded, you can use it for decoding. Whatever, like you can fit a batch of requests for decoding. So here, to reduce the model, whatever memory the model consumes, you use the quantization. So you use a lower, numeric and accumulation type to represent the model. So there are many quantization techniques, and the most used are the float 32 to float 16 and float 32 int 8. Like here, you basically try to reduce the memory consumed by the model, so you can squeeze in more batch, more requests, so it will increase the throughput. So as there are several algorithms for quantization techniques that are still improving. It's a good area of research. So here, like float 32 to int 8, like if you see the dimension of the numbers, like really getting smaller there. So you have to do it as lossless as possible. Okay, so this was like a big hit in the inferencing part. So it was introduced in VLLM, and it is called paged attention. Might be familiar with the like the working in what it was already there in the other systems. So here, okay, the LLM model decode, it's a sequential generation, right? And it is mostly memory bound. Like it is not computationally bound because you need the next token. You need the nth token to generate n+1 token. So it is a sequential process. You can't parallelize it so much. And for each token to generate, you need all the key value pairs, which is in the attention algorithm, right? Like k times kq by d transpose. Like you have the you want those values to be present in the cache of the GPU. So the key value pairs, there will be so many tokens, and all the key value pairs for the tokens will be stored in the cache. It is called a KV cache. And how do you try to manage the KV cache is the most challenging problem in LLM inferencing. So that basically, how do you handle this huge cache memory? So in older systems, what they used to do was, if you want to fit a sequence into the GPU, you want to store the input tokens, whatever the request the user send in, and all the output tokens to be generated. The user will also specify that I only want to generate 100 tokens for this sequence. Okay, so that will be another boundary. And if the request reaches a end of sequence token before the user specified, it can be taken out. Okay, or it will be forcefully taken out if it reaches the user specified limit. Okay, so whenever a request is added to the batch, the model will the GPU some continuous memory locations of the GPU will be assigned for this location, and no other request will be able to use this location even if end of sequence is reached earlier. Okay, so this causes a lot of internal fragmentation. Paged attention try to solve this internal fragmentation by using a lookup virtualizing, chunking the GPU memory into blocks and using a lookup table to find the memory. So the attention kernels had to be rewritten, but it gave better, you can now use the GPU memory with less internal fragmentation. Okay, and it was shown that only about 40% of the actual KV cache memory was utilized by the for inferencing. So this now with the help of page attention, you are able to use completely, like around 98% of the GPU memory is able to use for inferencing. So you can fit in more requests in the batch. It increased the throughput. By increasing the throughput, you eventually will increase the latency for a specific request rate. So this is a comparison. The orange line shows the other systems before the page retention, and the blue line shows the memory growth after page retention. Basically, you can fit in more batch size. The x-axis shows the batch size you can fit into the GPU. Okay, so whatever techniques we saw earlier was kind of trying to, increase the throughput, increase the batch size, thereby reducing latency. So we want the systems to be perform with minimal latency. So this is a speculative decoding is a technique which directly contribute to the lowering of latency. There are two methods for speculative decoding. The first one is a draft model. So you will use a smaller model, which is much less, in size in comparison with the your base model. It's called the draft model, and the time per output token. So being smaller, like you don't have much computation to get the sequence output right. So by the time the base model generate one token, the draft model can generate maybe 10 tokens. So basically the base model can either accept or reject the tokens generated by the draft model. So here you have a direct, lowering of latency if it accepts. It can also reject sometimes. So, and you have to train the draft model along with the base model to achieve the maximum, lowering of latency for speculative decoding. The second one is n-gram batching. So there are, tasks like summarization, document, question answering. Like these are input grounded tasks. Like you have a large prompt, and you are, questioning the model based on the prompt that you provided. Now, so here the idea was to, idea is if whatever the model is generated, so it matches with the just do a string matching, and if it matches with the whatever prompt has, so you use the data. So here also you can see a significant speed up, but this is only useful for input grounded tasks. Okay, now okay, so LLM model inferencing, right? This is you can dissect this process into two processes. The first one is the prefill, and second one is the decode. Prefill is when you are asking the model a question. So the model has to understand the question first, and then it decodes, right? So the key value pairs of all the tokens in your question has to be generated before the decode starts. Then only while the decode, and the model checks for the tokens and their attention scores, it will be present in the GPU. So suppose if you go back to the earlier continuous batching, right? Like whenever a request finishes the decode, you will have to add one more request. So before this request gets added, for the key value pairs to be present in the KV cache, you need to do a prefill of the request. So here now you have to store the decode phase. Like you are storing the decode phase for all the running requests. So this will affect the latency. So here in the chunk prefill, what you are trying to do is, when prefill is too large and you are without stalling, you are trying to chunk the large input prompt into smaller chunks and use it for prefill along with the decode. So here you are trying to eliminate the prefill stall, and it helps in decreasing the latency, so the better performance. Yeah. So I would like to talk about two inference engines. First one is a Hugging Face TGI. So the basic architecture of TGI is a server here, and internal queue, and a scheduler, and the GPU server. Okay. So whenever a request comes, the request gets tokenized and it is pushed into the internal queue. And it is the job of the scheduler, it's also called as batcher, like it will pull some request from the buffer and it will send to GPU for decode. So it is up to the scheduler to define like how many batches, decide how many batches will be fitting into the GPU for inference. Like whenever a request completes the decode, whenever end of sequence or the user provided limit is reached, when you take a request out of the batch, add schedule a prefill, all those decisions will be taken by the batcher. So it has it really become popular by the vast number of models it's supported. Okay, next one. Okay, so here so like okay, there are different scheduling policies in TGs. So the first one is the FCFS, which is the default policy in TGs. We also tried to experiment with the priority scheduling, like to serve for some category. You have some tiers of user like platinum, maybe gold, like who needs better lower latencies. Okay. This slide is okay. And the next inference engine is the VLLM.
How do you design a scheduling policy so that your performance SLA is met, right? A lot of usage of queuing theory, right? Priority queue implementation. So all that comes into picture. So it's a good research problem. A lot of synergies from other networking theory, and we can actually devise. So VLM is a very popular engine and most of the industry has moved to adopt it. And you see a lot of activity in the VLM repo, open source stack. And again, you can have a look at and play around with it. Yeah, thank you.
So regarding some experimentation, like if you have 3 users and you have single pod, how do you, schedule different users at different intervals so that you always give a priority to user 1 over user 2 and 3, like an increasing order. These are some experiment results we have. And this is the VLLM architecture. It is more or less like similar to TGI, where it also have an inference server, an internal queue, a scheduler, and the GPU processing part. Okay, here one change is like you can import the VLLM as a Python package and do an offline inferencing, or you can host it in a cloud or an infrastructure with GPU for the users to interact it with API calls. Okay, and here VLLM also comes with different policies like FCFS, first come first serve is the default policy, and we have user priority scheduling, earliest deadline first, and user priority with preemption. Preemption is when you already have a running request in the GPU. If a higher priority request comes, you take out the request from the GPU and insert the higher priority, even if it was already in the GPU memory. So now I would like to go into the monitoring parameters for inference. So now you have an inference engine and you want to monitor it continuously because you are paying for the GPU, on time basis, and you have to get maximum out of it. So you are consistently monitoring the throughput latency. These are the 2 parameters we have. And so in the throughput itself, we have two metrics. First one is the decode per second, and the second one is the prefill per second. Like as I said, like prefill is very compute intensive task. So it depends on the GPU hardware, and decode is memory intensive task. Okay, so both will be much different. So and you have latency. You have time per output token, which is the most common monitoring that you use. It also corresponds to the user satisfaction. Like you want the tokens to become as fast as possible. Decode time also depends on the size of the model, the batch size you are using, And then is a time to first token. It is actually queuing time plus generation of first token. So yeah, time to first token depends on the prefill throughput, because has to do prefill before generating the first token, right? So it is whatever time it's spent in the inferencing engine queue and the prefill and the total overall latency. Okay. So some slides are missing. Yeah. That's okay. Yeah. Four. This is 4, 5 is left. Yeah. But it is not required. I can use a keyboard if you want. Okay. What? How should I do it? Okay. Okay. So this is the future advancement and research opportunities we have. Like, as I said earlier, like KV cache management is the most important part here. Like the KV cache can, for example, one request, if it has a context length of 4000 and it uses a 8 billion model, the per request the KV cache size can grow to 2 GB. So in a 180 GB GPU, after 8 billion model was loaded, you can accommodate maybe 30, 40 requests. So that is a huge limitation. So we are trying to, quantize the KV cache. Many techniques are used there, and the computation optimization. Like for example, prefill is a compute heavy task, and decode is a memory intensive task. You can use, separate these two processes and use a specialized system for prefill and then decode. There are also some papers in this from Microsoft. And this is the hardware optimization. And IBM also provides fine tuning or inferencing specialized hardware like AIU. Then the cloud. Okay, so you might have multiple models and some users might be interested in very few of them. Okay, but you also want to give opportunity to any user who wants to use a rarely used model. So the serverless optimizations, okay, also comes there, and the power management. So the GPU has two clocks, right? One is a memory and the other one is the SM clock. Okay, so you can lower the SM clock so that the GPU will consume lower power because the decode is very less power intensive. Okay, so that way you can save the power. Okay, these are some research areas, and the user experience is like, you can model the users for and those areas are of huge importance here. And the performance and power trade-off, like you can use a lower power GPU or a lower hardware GPU to serve the rarely used models. Yeah, and also the coming to the third one here, like you want the predictive tools, to support the user. Like some suppose you like you ask you have a platform where a user can bring their model, and user doesn't know what hardware to use and when to use, right? Like you can so for a question like, for these many users, what GPU should I go for, or what for my requirements, what model I should use? So you can have a decision support system for this. Thank you. Like, do you guys have any questions?
Yeah, we can take a few questions. Any questions?
Hey, hi. It was an interesting talk. So I have actually two quick doubts. One is related to the batching. I just want to know, is it batching along what axis? Is it like a batching of the users or batching of the tokens?
Batching of the request.
Batching of the requests.
Like suppose you have 10 users, maybe 10 of them simultaneously send you a request, right? So you have GPU which can process all the requests in parallel. That is the advantage of using the GPU. Right now, you can pack all the 10 users together. Here, like maybe one user sent you 2 requests. Now, but in the granularity, it comes to the packing of requests.
Got it. So it's a batching along the request.
Yeah.
And second quick question is like, did we assume that all the GPUs have the same compute power?
Where?
All the GPUs have the same compute
No,
power?
it is different. So there are multiple models from NVIDIA itself, right? For example, the data center versions like A100, V100, H100, and if you consider the gaming GPUs like GTA 1080 or
In terms of different GPU specification, you can put it right in the user sector. You also have virtualization capability. The same GPU resource can have slices of it, which you can configure large size, medium size, small size, and then you can apply this.
those
So the
are like
policies
the
we are
multi-
proposing are based upon like heterogeneity of the GPUs.
Yeah.
Got it. Thank you.
So that online,
There is only one online.
okay.
Yeah. Nishant Tiwari is asking that how to achieve balance between quantization of a model and its accuracy in response generation, and what's the margin or response deviation from the quantization of models?
Okay, so this depends on the what algorithm you are interested in. Like, for example, there is a trade-off. For example, float 32 to float 16. There is a trade-off, and the trade-off will be much higher if you go for in-date. And you don't specifically use select one quantization. You select it because your GPU hardware also supports it. So most cores of the GPU, if you see the data center grade GPUs are float 32. Like you will have less number of in-date or float 16 processors, but you do it to save memory, but at the cost of some performance degradation.
Thank you.
When we talk about the distributed memory systems, the KV cache, I suppose, is local to the block, right? It's the local memory in the block, like of the GPU.
So in DRAM,
Yeah.
it is in local to the DRAM. Yeah.
Yeah. So then when we do that KV cache management, like how does it load the data? Won't there be too much communication overhead and over there?
Get your question.
So like it's local to the block,
Yeah.
which has its own shared memory. And then it takes up when you submit for a request, I assume it takes from
No,
the global.
KV cache is in the GPU DRAM.
Yeah.
Yeah. So you have to move the memory to the register of
Yeah,
the SM.
Yeah.
Okay.
Yeah, exactly.
Yeah. Okay. So NVIDIA uses I think it is internal to the chip. It will be really fast.
Okay.
But
okay.
if you use tensor parallelism, you have to transfer the weights from another GPU, right? Like
Right.
if you use tensor parallelism.
Communication.
So if the if the both GPUs are on the same node, the communication will be through
Fast.
NVLink and it
Yeah.
will be really fast.
Yeah.
But if you have a GPUs which are on separate nodes,
Mhm.
then the communication overload will kick in.
Yeah. But then when you manage the request over there, how does it work actually inside that?
Okay. So
No, I think from CPU to GPU, you have to have fast link because the request coming and
yeah.
buffering up in the CPU.
Mhm.
Then you need to transfer to GPU.
Yeah.
So is your question related to
Yeah.
CPU to GPU?
CPU to GPU, yes.
Yeah, I think that PCI.
or PCI, cables
yeah.
those are really fast. You can't avoid those communication overheads
Okay.
because I think it is in few GBs per second is the communication rate.
Yeah.
And also you do multiplexing, like when the communication, like the communication happens when there is processing is going on, right?
Mhm.
Like you preload the data.
Okay.
So GPU has multiple layers of cache.
Yeah.
So I think L1 and L2 cache is there before the DRAM.
DRAM.
So the we hope the data to be present in the
Okay.
cache.
Okay.
Already
okay. Got
present.
it. Got it.
Yeah, but it's also like it's evolving. The host to GPU connectivity and high bandwidth, all this actually increasing day by day with the better technology, right? Hardware technologies in place. Yeah.
Thank you.
Okay, so I think we can wrap it up. So we have yet another 2 set of sessions coming, right? One will cover in depth all the Granite suite of models that IBM offers. And also the last session, even more interesting for you to see the application point of view, which Dipti will be covering. So I encourage you to join the next set of session post lunch. Please do not go away. Thank you.
And
Yeah.
before we close, we wanted to give a token of appreciation to all the speakers from the morning session. So maybe we'll start with the first session. Pratibha. Thank you. Abha. Lunch will be served in the same coffee hut. Please continue the conversation or walk around campus, but please come here by 2:15. We'll be starting the sessions at sharp 2:15.
Picture of all the speakers.
Yeah.
Yeah.